Hello, hello, hello. Hi, hi, hi. Good morning. Let's look at one more theorem, one more example, and then we will be done with 1.6. We've got this theorem, 1.17, the basis for the row space, which says if a matrix A is row equivalent to an echelon matrix F, then the row space of A is equal to the row space of F, and the pivot rows of F make a basis for both row A and row F. And that's different from the previous one. The previous one says the pivot columns of A are a basis for the column space, but with the row space, it's the pivot rows of F. Okay, so we're just going to use one example as like an illustration of why this theorem is true. And it's still the same matrix F and A from before. I'm just going to take a quick screenshot so we can just have a reference to see why we're doing this notation this way. Okay, just so we have it in our field of vision, I put the matrix A right here, and I'm using Greek letters to denote the rows. So here's the row 1, -5, 0, -1, -2, but we're writing it as a vector. So I always like to write vectors as a vertical column. And likewise, phi represents a row of the matrix F. So Greek version of F there. Okay, so first of all, let's explain why the row space of F is a subset of the row space of A. So we know there's some sequence of row operations that will reduce A to F. Let's just say we do a row operation to A to get some other matrix B, clear out some non-zero entries below pivot positions, etc. And we do that a few times and end up with the matrix F. Well, at each step, each one of these row operations is either a multata placement operation or scaling or a swapping operation. And each one of those is going to make the rows of the new matrix each some linear combination of the rows of the previous matrix. So multata placement replaces one of the rows with the sum of itself in another row. Swapping two rows, well, you're not changing them, you're just making the new rows equal to 1 times one of the other rows plus 0 times the rest, and that's still a linear combination. If you scale a row, then that replaces that with a linear combination of one previous row. So at every step, the rows of B are a linear combination of the rows of A, and the rows of C are a linear combination of the rows of B, which is just a more complicated linear combination of the rows of A, and so on. So yeah, all the rows of F are linear combinations of the rows of A, and we can say that linear combinations of the rows of F are linear combinations of the rows of C, which are linear combinations of the rows of B, and so on, all the way down. You're just getting more complicated linear combinations of the rows of A every time you do one of these row operations. Okay, so that's A. Let's look at B. B is the same idea because row operations are reversible. So F can be row reduced to A, and so rows of A are linear combinations of rows of F. Okay, so every row of A can be written as a linear combination of the rows of F, and every linear combination of the rows of F can be written as a linear combination of the rows of A. So these two things together imply that the two matrices have exactly the same row space. And this is not true with the column space. The column spaces are not equal, as we saw in the last example. But let's look at what C says. C is basically saying prove the rest of the theorem. We already got row of A equals row of F, and we want to show that the pivot rows of F make a basis for that row space. Looking at the rows of F here, a non-pivot row is by necessity got to be the zero vector, which is always a linear combination of everything else, and you can always throw out the zero vector. So to show that we have a basis, we already know that the pivot rows will span the same subspace as if you include zero. But to show that it's a basis, we just need to show that they're linearly independent. And to do that, we're just going to notice where the pivot positions end up being. Just like you had in F, the pivot positions are the only non-zero entry in its column of F. Now it's the only non-zero entry in like the row of this transposed matrix. So the pivot columns cannot be written as linear combinations of each other, which makes them a linearly independent list of vectors. And so we have a basis. It's linearly independent, and the span of just the pivot columns still spans the whole row space because we don't need to include the zero vector. Cool beans. I will see you guys later. Got some good exercises coming up. Take care.